So in the last lesson, I introduced you to Faraday, and in this lesson, what I want to do is introduce you to Faraday's law in a little more rigorous detail. Going back, you can remember what happens is if I take a magnet and introduce it to a coil here, I can induce a current in that coil. And it's while the magnet is moving that this happens. And obviously, as I push the magnet in, the current goes one direction. As I pull it out, goes the other way. So it's this changing magnetic field in the presence of a wire loop that is critical to Faraday's law. Let's look at this a little more detailed here. I've kind of schematically diagrammed my magnet there, and you've got the field lines coming out of it, those light blue lines with arrows pointing away from the north end and going to the south. Keep in mind that all those eventually wrap back on themselves. There are no end points to magnetic field lines. It goes through the bar magnet and comes back again. So they all go out a far distance and come back around. I've got diagrammed over there a simple single loop of wire that is coming out of the screen or going into the screen, whichever you want to look at it. I've cross-sectioned it so that we've got the wire coming toward you and going away from you in a ring there. Now, as I bring the magnet over, what's going to happen is the current flow is going to increase as that north pole of the magnet goes in, but then it'll stop once the magnet stops moving. And if you think about it, those lines of field are being cut in two, if you will, by this coil of wire that's sliding onto the magnet there. What's happening is I've got flux that I'm shoving into that coil. That loop of wire has magnetic flux lines that are magnetic flux because of the lines of field that are passing into it, and that flux is increasing. And as long as it increases, I have current flow. Likewise, if I pull back off, now what's going to happen is the current's going to flow the opposite direction, but taper away as I get further and further away. So it's only while the flux is changing that I get this current flow, and the direction of it has to do with whether the flux is getting larger or smaller. Am I pushing more field into the loop, or am I pulling the field out? So let's get a little more careful about this. I'm going to give you a specific example here of a magnetic field uniform across the screen there, pointing into the screen away from you. So you're looking at the tail ends of all the field lines. And I'm going to have a wire that is part of a large loop, and the left side of the loop is going to stay off the screen, but the right side of the loop is going to slide in here. And as it does, I want you to think about the vertical section of wire. If I'm a positive charge sitting in that vertical section of wire, I'm moving in with a velocity v. That velocity is going in the x direction, if you will, from left to right across the screen. Take your right hand rule. If I'm a positive charge moving from left to right across the screen, the field pointing into the screen, lay your hand palm face down on the screen and your thumb is sticking up. So those positive charges are going to have a Lorentz force on them that shove them to the top of the loop. There's going to be a QVB that pushes all the positive charges up and the negative charges down in that vertical chunk of wire as it slides in there. So this time frozen photograph that I've got right now, I'll have positive charge piling up at the top, negative at the bottom. Those two wires can go off to the side, and maybe there's a light bulb or something like that out there that they could run through. But for now, let's just think about the positives going up and the negatives going down. The same effect would actually be had if I had an electric field there. And in fact, since it's equivalent, we can go ahead and say what I've done is I've induced an electric field that is pulling these charges around. Notice Q shows up on both sides. The force is QVB because of Lorentz. The force of Q times E because the electric field is induced. Divide the Q's out, and I can also think of this in terms of, instead of an electric field, I can think of it as a voltage that is driving these charges. So I have an induced voltage, and voltage is the field times the length. So take the length over to the other side, and I have that the induced voltage is V times B times L, where V is the velocity of the bar as it slides in from left to right, B is the field strength, and L is the length of the bar. Now, I'm going to tell you the book actually uses this V sub IND, the induced voltage. I don't really care for it, and a lot of books don't either. The more appropriate way of saying this is it's called an EMF, an electromotive force. And the reason for this is because V, the potential, is usually thought of, it's defined initially in terms of potential energy. And potential energy can only be used when I have a conservative field. And this is no longer a conservative field for reasons I'll get into later on. But for now, what I'm going to do is I'm going to use that kind of script E there to represent the EMF, and functionally that works just the same as a voltage. If I had a light bulb off to the left side of the screen right now, This E here would be the voltage that would be driving current through that light bulb. It'll be more clear later on, hopefully, but for now, the EMF is equivalent to a voltage that a battery might produce, except for now, the EMF is the electromotive force that is being made by the Lorentz force law, or more accurately, because of Faraday's law. So let's go back and see if Faraday comes into this. I've got my VBL is equal to the EMF. And I'm going to go ahead and point out to you that V is just really the dx dt, where x represents the position of that vertical chunk of wire. Now, since B and L are both constants, I can go ahead and throw them into the integral, the derivative as well. So d dt of B times x times L is equal to this EMF. And also, I'll point out to you that x times L just really represents the area that is currently in the field. So I have B, the field strength, and A, the area that is in the field for this loop of wire that I've got. Now, B times A, if you'll recall, is related to the flux. In fact, in this case, it's the negative of the flux. Negative because B points into the screen, and A, in the way I've drawn it here, would point out of the screen. So what I have is the EMF is negative d phi dt, where phi is the magnetic flux through this loop. What's covered in that yellowish area with the red crosses going into the screen. Now this is Faraday's law. The EMF is negative d phi dt. This EMF is induced equal to and opposing the time rate of change of the magnetic flux through any loop of wire. And I can do this either by changing the field strength, or changing the area, or just changing the angle between them. Because after all, the magnetic flux, phi sub b, is going to be the integral of b dot dA over some surface. Or for simple cases, if things are constant enough, I can say it's just b times a times the cosine of phi, and therefore change b, change a, or change phi, and I get a change theta, and I get a change in phi, and therefore I get an EMF. I can either have the area increasing, as I just did in the example I showed you, or I can have the field increasing, as I did when I shoved the magnet into the loop, or I could have the angle changing, which I haven't done yet, but is pretty easy to think if I took the magnet and flipped it around near a loop. All of these are important because, once again, they give me a way of taking motion and turning it into an EMF, which then drives a current, which I can use to do electrical work.